Okay, so identifying hybridization in a small molecule is getting you to use valence bond theory, which is basically a way of taking the shapes of atomic orbitals that we learned in quantum and trying to explain the shapes of molecules that we actually observe from VSEPR theory. Okay, so when you get to things like tetrahedral electron group geometry, how do you form that 109.5-degree bond angle from overlap of p orbitals, which we know are at 90 degrees to each other? So we form these new hybrid orbitals where the electrons are actually being shared, because it makes sense that they're not being shared in an orbital that belongs to just one atom. Okay, they're being shared between two atoms, so it makes sense that they may actually exist in different space to what we derive for just an atom. So hopefully we remember enough from quantum to know that each atom has an s orbital for each value of n, right? So thinking about Lewis structures, right? Lewis structures are talking about s and p valence electrons overlapping, right? That's where we get the octet, right? Because we have one s orbital, which can contain up to 2 electrons, and then we've got 3 p orbitals that contain 2 electrons each. That's a total of 6 in p orbitals. So if I was to draw my p orbitals, and this is going to look rough, I do apologize, they're kind of like a dumbbell kind of shape. So we're going to call that the px, okay, with the x-axis being like our linear axis along which we're bonding, and then the py is going to be vertical, and then the pz, this is going to be hard to draw, but I'm going to try. Oh, you know what, I'm going to go freestyle for this. It could be so the z-axis then will be in front and behind right here. Okay, so we've got 3 p orbitals. Okay, so think about how we can mix s and p orbitals together, and you have to have at least 2 to start with, okay, to get a steric number of 2. The number of orbitals needs to match your steric number, okay? So these are our hybrid orbitals. So what do you get if you mix 1s and 1p? Well, you get a hybrid orbital, and we're going to call it an sp hybrid orbital because it comes from mixing 1s and 1p. And just as an FYI, if you've taken like 1 p orbital, you've still got 2 left over. So potentially you have 2 p orbitals left over, which can overlap above and below the plane of where the bond is being made, or in front and behind where the bond is being made, and that is what leads to your pi bonds, okay? So theoretically, if you have sp hybridization, you could be forming, well, 2 pi bonds in total. So this is where triple bonds are coming in, trying to make that link to organic chemistry. So that is lateral overlap, above and below, or in front and behind the bonding axis. And the bonding axis is where you get your sigma bonds forming, right? Because they are directly where your bond is being formed. Okay, so then if we have a steric number of 3, we're going to need a total of 3 hybrid orbitals. So we only have 1s, but now we can take 2 p orbitals. So we show that with a superscript p squared, I guess, right? So it's telling us we have 2 p orbitals mixing with 1 s orbital. And just as a side note, that means you still have 1 unhybridized p orbital left over. So again, that can form up to 1 pi bond. Okay, so that's where you can get a double bond coming from. Okay, so then tetrahedral, you're going to have to use that 3rd p orbital, so that is your sp3 hybridization. So you would expect no leftover p orbitals, so you wouldn't expect anything that's sp3 hybridized to be forming double bonds, okay? But then what happens? You've run out of s and p orbitals. So to explain trigonal bipyramidal and octahedral electron group geometries, what we actually do, and this is the same kind of explanation for expanded octets in Lewis structures, is that we would have to use low energy d orbitals, okay, to have somewhere for those bonding atoms and lone pairs to go. So that would be sp3 and then 1d. Okay, so sp superscript 3d would be for trigonal bipyramidal, and then for octahedral it'd be sp3d. D, and we need 2 of those. Okay, so those are the other 2 hybridization schemes. So long story short, okay, all those hybrid orbitals kind of look the same in terms of like it's a mixture between an s and a p orbital. So a hybrid orbital is going to have like one little lobe and like one big lobe, kind of thing like that, and they'll be oriented in the directions that correspond to the ideal bond angles for that correspond to your steric number. Okay, sorry, that's a kind of rough picture, but you get the idea. So the quick and easy way to relate your electron group geometry to the hybridization scheme is just add together the indices or the power in your hybridization scheme, right? Remembering you start at S until you've used up all the S orbitals, then P, and then you have to add Ds if necessary. So a steric number of 2, those hybrid indices should add up to 2. So S plus P, 1 plus 1 is 2. Steric number of 3, so 1s plus 2 p's, 1 plus 2 is 3, right? Steric number of 4, 1s plus 3 p's, 1 plus 3 is 4. Steric number of 5, 1s plus 3 p's plus 1d, 1 plus 3 plus 1, 5, right? This is the easy way to remember it, right? Steric number of 6, 1s plus 3 p's plus 2 d's, 1 plus 3 plus 2 is 6. Okay, so for any of these kind of questions, just don't forget you have to draw the Lewis structure first, which means you have to start counting valence electrons every single time. So don't just look at that and say SCl4. Oh, there must be 4 SCl bonds, so it's probably tetrahedral in it, right? Let's find out, right? Okay, so we've got 4 chlorines. Each of those have got 7 valence electrons. So that's 28 plus 6. That's 34 valence electrons we're looking for in our Lewis structure. So sulfur in the middle, chlorine around the outside, around the outside, around the outside. Join them up with single bonds and complete the lone pairs on the chlorine. See what we got. Where's my line? There we go. Right, bond, 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 James Bond. All right. Blah 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 blah. Right. 1, 2. Right. So let's count up our valence electrons. See if we can get to 34. So 6, 12. I can't draw as fast as I can count. 18. Some of them are big, some of them are small. It's cool. 24. And then 26. 28, 30, 32. Oh no, we've only got 32 valence electrons. What does that mean? It means sulfur has to have a lone pair, which means it has an expanded octet, which means when we calculate our steric number, that is 4 bonded atoms plus 1 lone pair, which means we've got steric number 5, which means our electron group geometry is trigonal pyramidal, bipyramidal, even bipyramidal. Okay, so as an FYI, although you don't need it to answer this question, the molecular geometry will then be seesaw, okay? Because if you have a trigonal bipyramidal electron group geometry where one of those groups is a lone pair, that's what we call the seesaw or sawhorse if you prefer molecular geometry. But we don't actually need that to get our hybridization. Hybridization comes straight from your steric number. Your steric number is 5, so it has to be sp3d. If I could get my mouse to work, sp3d. And if you're not sure, add them together. 1 plus 3 plus 1 is 5, which matches my steric number. Okay, so hybridization, the most foolproof way to do it is that your hybridization comes straight from the steric number to make sure you're not forgetting to count lone pairs of the central atom, because they need a place to live too.